Okay, welcome everyone to the PALS seminar. Today we have CU Boulder's own Peter Mayr talking about finite nilpotent semigroups. Peter, take it away.
Thank you. Thanks for coming back for another semester of PALS. So I'm going to talk about the commutator theory for semigroups, or the little that we know about it. Just to start with, concepts like commutator theory is one of the basic tools for structure theory of groups, right? So concepts like abelian groups, nilpotent, solvable groups, all around. But those words get rarely used for semigroups, so it's unclear what even a solvable semigroup should be. Now, of course, general algebra, universal algebra, it gives us an answer for that. So there is a definition of a commutator that's generalized from the commutator of normal subgroups of groups. For arbitrary algebras, we have a commutator of congruences, alpha and beta. It's sometimes called the term condition commutator that was developed in the 1980s. And the definitions are a bit technical, so I want to hold back on that. Just to give you the principal idea that guides this definition is the observation, the premise that an algebra A is abelian if and only if the diagonal, the set of all pairs AA for A in A, forms a class of a single congruence on the square of the algebra. So this corresponds to the observation that a group is abelian if and only if the diagonal, so the set of all pairs GG, form a normal subgroup in the direct product G times G. Okay, so this looks like a random fact, but starting from this premise, people have indeed developed a workable definition of commutators of arbitrary congruences. And if you have that, then you can, of course, say, when we denote one for any algebra A, we will denote one as the total congruence on this algebra, 0 the trivial congruence or equality on A. And we can say an algebra is abelian if the commutator of 1, 1 is equal to 0. And like saying that the derived subgroup of the abelian group has to be trivial. You can iterate the commutator to define solvability by saying commutator 1, 1 with commutator 1, 1. Take the commutator of these two things. If that it's trivial, then we will call an algebra 2 solvable. Can also define nilpotence doing this iteration commutator 1, 1 with 1 is 0. And there is another more recent definition of higher commutators that gives a different generalization of nilpotence from groups. It's called supernilpotence. I'll talk about a bit later. So again, we will say algebra is 2 supernilpotent if the ternary higher commutator of the total congruence with itself becomes trivial. All right, so this is just, these concepts exist, right? They are well defined. You can read up on them in books. I'll show you some the technicalities of these a bit later, but just to some kind of motivation first, I want to show what what is known. What do these concepts mean in the case of semigroups? And then you will decide for yourself whether these concepts are useful for semigroups, right? And whether you are interested in seeing the technical definitions, or whether you want to stop this talk early. Anyway, so already in the 90s, Vaughan characterized abelian semigroups. Actually, his characterization is just he gave a construction method, a parametrization of all abelian semigroups. Bands are idempotent semigroups, so where every element is idempotent. They turn out to be abelian, nilpotent, or solvable. All means the same for a band. The band has one of these properties if and only if it's what's called a rectangular band. So this is very almost a trivial one, a direct product of a left zero semigroup and a right zero semigroup. Inverse semigroups are quite popular. They are close to groups, generalizations of groups, and sometimes called semilattices of groups. And it is not hard to see that for those, whenever they are solvable or nilpotent or abelian, then those inverse semigroups actually are groups having the same property exactly. I've looked at monoids some years ago. It turns out a monoid is abelian or nilpotent if and only if it embeds into a group having the same property. I do not know what solvable monoids are or supernilpotent monoids are at this point. Nebojsa-Modrinsky and Jelena Radovic from Novi Sad, they studied, considered semigroups that have a zero element, that absorbs every other element under multiplication. And they showed such semigroups with a zero, they are abelian if and only if the multiplication is trivial. Right? So S squared, any product of two elements is zero. And they are nilpotent or and equivalently solvable if and only if every product of a fixed length, say n, becomes trivial. So these are what's called classically the nilpotent semigroups in semigroup theory, semigroups that satisfy S to the n equals 0. In a separate paper, they also investigated what's called Riesz matrix semigroups. So these are kind of the building blocks of semigroup theory. If you haven't seen that, let's see. Maybe I can try to make this. Oops. Vanish. This one. So a Riesz matrix semigroup is built up from a group and two sets I and lambda, and a matrix P, where the rows and the columns are indexed by I and lambda, and the entries come from group G. Then the universe of such a Riesz matrix semigroup consists of triples from I G lambda, where we multiply two such elements, two such triples, by just taking the first index I from the first vector, the last index mu from the last vector, and the group part in the middle, you'd be tempted to just multiply G times H, the group parts, but it's not quite that simple. There's that you insert an element from this so-called sandwich matrix P, namely the element at place lambda j between G and H to get this multiplication. So these are completely simple semigroups, kind of the building blocks of semigroup theory. And Nebojsa and Jelena showed that such a thing is abelian if and only if it's a direct product of a group with, again, a rectangular band. It's nilpotent if and only if the group that goes into the Riesz matrix semigroup is nilpotent, and it's solvable if and only if the group is solvable. So what I did recently last year is concentrate in particular on finite semigroups. It turns out they have one of these four properties: abelian, nilpotent, supernilpotent, or solvable, if and only if they are nilpotent extensions of such a Riesz matrix semigroup. So what's a nilpotent extension in semigroup theory? We say S is a nilpotent extension of an ideal M if long enough powers of products of elements in S fall into M. So, so this is an overview of what we know about these concepts in broad classes of semigroups. I'll go into the details of some of these results later in the talk, but just the overall idea that I want to convey here is that these conditions are very strong. Like abelianness or nilpotent solvability, they are very strong. For semigroups, they essentially force the semigroup to be very close to groups or have a very trivial idempotent structure. So, this is a broad overview, and now let's get into the gruesome details of defining what the commutator is. So many people in 1980s worked on generalizations of commutators from normal subgroups to arbitrary congruences, like Jonathan Smith, Hans-Peter Gumm, Hermann. You'll find development treaty on survey on this in the book by Fries and Mackenzie, commutator theory, that I'm referencing here. So instead of a group, we have an arbitrary algebra. Instead of normal subgroups M and N, we have congruences alpha and beta. And then we are going to define a subalgebra of 4 tuples, which, as you note, M alpha beta. I'll write these 4 tuples in squares, the subalgebra of a 2 by 2. That's generated by 2 types of generators. The first one contains in its columns pairs AB that are alpha related. And the second type of generators contains in the rows pairs CD that are beta related. So that's M alpha beta. The operations are just pointwise. There's no matrix multiplication floating around here. And then the commutator alpha beta, the commutator of those 2 congruences, is just defined as the smallest congruence delta of A, such that for every square in M alpha beta, whenever the first the entries in the first row are delta related, then also the entries in the second row are delta related. So this is often called the term condition. This implication has to be satisfied, and it allows us to find the smallest congruence. This gives us the definition of the commutator of alpha beta. So the nice thing about this definition is that it works for arbitrary algebras, that it's independent of the operations that we have, does not rely on the usual group theoretic commutators, X inverse, Y inverse, XY, stuff like that. And it turns out to, this weird definition turns out to describe exactly for groups the commutator of two normal subgroups, M and N. The bad thing about this general definition is it's hard to apply for concrete algebras or concrete examples, for example, for semigroups. So I just maybe I should stop for a minute if there are any questions throughout the talk. Please just speak up out there. I can't see all of you, but feel free to interrupt me at any time. So if you haven't seen this definition before, it's a bit much to take in. Let's look at some concrete examples, maybe to get some kind of feeling for this. I've copied the definition at the top of the screen here for you again. But let's just concentrate on a very nice semigroup natural numbers under adhesion, right? And I want to compute the commutator of the total congruence with itself there. So what do I have to do? From the definition, I have to look at this algebra of squares, M11. So here, this one again denotes the total congruence on the natural numbers. So it's generated by two types of generators, right? Those AABB and CDCD, where now A and B are in the total congruence and C and D are in the total congruence. So this is no restriction on them, on those elements at all. But what can we generate from these guys under addition on the natural numbers? Because addition is commutative, everything that you get as a sum of several elements of this form can be written just as a sum of two elements, like that. Yeah? Can simplify it. And then you see, if you want to check the term condition, you'll see that whenever the entries in the first row are equal, this just means that C and D are going to be the same. Then clearly also the entries in the second row are going to be equal. So, okay, that's what I just said. If the smallest congruence that satisfies this term condition is just the equality relation. So this shows that the commutator of 1, 1 is trivial equality relation. Right? So maybe to the surprise of no one, we proved that this semigroup N with plus is indeed an abelian algebra under this definition. So maybe just give you another example where things work out a little bit differently. Let's look at the two elements semilattice 0, 1 under multiplication. So all products are 0 except 1, 1 is 1 times 1 is 1. So again, I want to compute the commutator of the total congruence with itself. I'll denote it by 1 sub s here just to distinguish it from the elements one in the semigroup. And notice that among the generators of M11, I have those two matrices clearly. And if you multiply them together, you get the matrix that's 0 in the first row and 0, 1 in the second row. Now, the pair 0, 0 is clearly in every congruence, even also in the commutator, which implies that the pair 0, 1 has to be in the commutator as well. So what we see from this here is the commutator of 1, 1 for this semilattice is the total congruence again, because we have 0, 1 in there. So this semilattice multiplication is commutative, but this does not imply that as an algebra this is abelian. In fact, it's a non-abelian simple algebra. Somehow counterintuitive, maybe if you see it first. It's what's called a snag in the lingo. All right. Any questions about these examples? So this is just simple applications, what you do in order to compute the commutator of congruences. So maybe just to observe. Oh, what was that? Sorry, I got some technical issues here. Where is my slides?
I think hide meeting. Or right next to AI.
Oops. Thank you.
That's the exact opposite. I thought it might.
So I just want to point out, you can extend this example easily to show that in semilattices, the commutator of any two congruences always boils down to just the intersection of those two congruences. Right? So this just means that for semilattices, the commutator operation is not useful. It doesn't give you anything new that you don't or can already compute by intersection. Okay, not sure I got this. Maybe like this. So I want to mention a few properties of the commutator for general algebras. Like groups, it's monotone in both arguments. The commutator of two congruences is always contained in the intersection, like for normal subgroups of groups. The commutator plays well with restriction to subalgebras. So if you take the commutator, if you have B a subalgebra of A, then the commutator of alpha and beta restricted to B is the same as the commutator of alpha with beta in the big algebra, and then restrict that congruence to B. With, you get a less than or equal here, similar as for groups. This I want to point out this third property because it guarantees, for example, that if you have an abelian algebra where the commutator of the total congruence with itself is trivial, then this also holds for every subalgebra. So it's a very reassuring thing. Subalgebras of abelian algebras are still abelian, always. And conversely, it has a implication for semigroups. In particular, if you have an abelian semigroup, it cannot contain anything non-abelian like a non-trivial semilattice. Right? More generally, a solvable semigroup cannot contain any non-trivial semilattice, which means that usually people in semigroup theory, they study the idempotence of a semigroup. They are ordered, and there's a natural order on them. But this means for semigroup people that in a solvable semigroup or a nilpotent semigroup or a abelian semigroup, all the idempotents, they are pairwise incomparable. They are all primitive. Okay. So it's a very strong condition. Then I just want to point out that in congruence modular varieties, like groups, rings, loops, or lattices, more is true than these general facts that I mentioned before. Also, the commutator permutes, so it's symmetric. Alpha, beta is commutator beta alpha. This is not clear from the definition of the commutator. This is very non-symmetric. Also in congruence modular varieties, the commutator distributes over joins, and it behaves well with respect to taking quotients. All of these nice properties that help you compute commutators may fail for semigroups, and so there are counterexamples for that. I just want to emphasize the third property, which is number 6 here. We've already seen in our examples that the semigroup N under addition was abelian. Now we can find a congruence there from the ideal of all the non-zero elements in N. If you this forms an ideal, and you can do what's called the risk quotient, factor out the semigroup by the ideal of non-zero elements. So you got a congruence with 2 blocks, then one containing all the elements in the ideal, and another block containing the single element which is not in the ideal, 0. And you look at it and you figure out this is a 2-element semilattice. So this quotient is isomorphic to a 2-element semilattice, which we checked is not abelian. So we got this very disturbing behavior with an abelian algebra, but a quotient of it is not abelian. So this can very well happen in semigroups. Okay, that's what I just said.
Peter, can I?
Yeah.
Marcel here. Can I ask you a quick question? Just, I thought before you said that a Rees matrix semigroup provided that the group, say if the group was trivial, for example, if the group was abelian, then that was abelian. That has a substimulus.
I'm sorry, I didn't quite hear what was the end of the question?
My dog keeps on barking. Well, with the Rees matrix semigroup example, I thought maybe I misunderstood. I thought you said that was abelian, provided that the group was abelian.
That can happen, right? But in the Rees matrix semigroups, also the idempotents, they are incomparable, right? So you don't have any semilattices in there.
Yeah, but you have like a idempotent and 0 is a semilattice.
No. So I meant not the completely zero simple Rees matrix semigroups, but just the completely simple ones without the zero.
I didn't see it. Okay. Yep.
Yeah.
Thank you. I'm glad I asked so that I wasn't confused there. Thanks.
All right. So let me talk about nilpotence in general, and then for semigroups as well. So note that because commutator is not symmetric, alpha beta is not the same as beta alpha, you can define two different lower central series for considering nilpotence. We'll say you can do a commutator 1,1 with 1 on the right, and then iterate this by adding commutators with 1 on the right. So this is what if this series stops after n plus many steps, then we will call the algebra right and nilpotent. And dually, you can do this thing on the left. And in general, those two won't be the same. Of course, for any algebra, right one nilpotent and left one nilpotent is the same. This is just abelianness. One commutator, one is 0. And I also want to point out that it's always true that abelian implies n nilpotent for any n and bigger than 1 and n solvable of degree n for any n. Anyways, so just to mention this result about nilpotent semigroups in general are not classified, but nilpotent monoids, they are kind of easier to understand. So monoid is just a semigroup with an identity element, multiplicative identity 1. Then for such a monoid and the natural number n, the following are equivalent. Semigroup is left and right nilpotent if and only if it's cancellative and right nilpotent. So cancellative just means for what you think it does. If you have x times y equals x times c, and this implies that y is equal to z. And conversely on the other side. This is equivalent to saying the semigroup is cancellative and satisfies some equation Qn xyz equals Qn yxc. These equations are iteratively, inductively defined down there. And the important thing is this is equivalent, this nilpotence in the general algebraic sense is just equivalent to saying that this monoid embeds into an nilpotent group. So it's a subsemigroup of a nilpotent group. Now, the equivalence of 3 and 4 is a very classical result by Maltsev from the 1950s, and it was rediscovered, I guess, by Neumann and Taylor in the 60s. They characterized which semigroups can be embedded into nilpotent groups. And there are several of these families of equations that are necessary for that. So because of time, I'm probably not going further into that. Yeah, so everything is quite under control here for nilpotent monoids. So I wanted to talk about really higher commutators and supernilpotent semigroups. I guess in the last 15 minutes or so, let's try to introduce those higher commutators first. So probably worthwhile to think of. So I want to define the commutator of, say, 3 congruences, alpha 1, alpha 2, alpha 3. Let's compare how we handled 2 congruences. What we defined the subalgebra of A to the 2 times 2, whose elements were kind of squares. where entries with two types of generators, entries in the first type of generators, the columns were alpha related. The second type of generators, the rows were beta related. And now we are going to add more dimensions to this picture for higher commutators. So if I have three congruences, then instead of having these squares, I'm going to have cubes. And I'm going to have three types of generators. I'm trying to just visualize this with these pictures instead of giving you the writing down the entries. So the first type of generators, we got these vertical edges that are blue. They all denote elements that are alpha 1 related. So every one of this blue edge contains the same element A1, B1. Okay? In the second type of generator, go in the other dimension forward. These green edges always denote, pair A2, B2, that is alpha 2 related. And for the third type of generators, the horizontal edges, the orange one, every orange edge is A3, B3, which is in alpha 3. So you take these kind of generators, close them under the operations of your algebra, and what you get is now M alpha 1, alpha 2, alpha 3. There's a subalgebra of 8 to the 8. And how do you define the higher commutator? A ternary higher commutator of these congruences is just the smallest congruence delta, such that for any cube in M alpha 1, alpha 2, alpha 3, we have something like the term condition. So previously, for the binary commutator, the idea was if the first row was delta related, then the second row has to be delta related as well. So here the idea is if every horizontal edge but one are delta related, then this last edge is also have to be in delta. So you're looking for the smallest congruence that makes this implication true for all cubes in M alpha 1, alpha 2, alpha 3. Okay, so that's the definition of ternary commutator, which is due to Bulatov from the early 2000s originally. You can imagine how this can be generalized to more than three congruences, that you just have to consider hypercubes of dimension 2 to the k. And the basic properties of these higher commutators similar to what we've seen in the binary case already. I want to point out that in general, the k-array higher commutator is not expressible as an iteration of binary commutators. So it is really something new, except if it's not. In the case for groups, it trivializes. The k-array commutator of k normal subgroups in a group can be expressed. It's just the iterated binary commutator on all permutations of these normal subgroups and take the product of those. Right? So for groups, the higher commutator, you haven't learned it in your algebra course because it's nothing new. Right? So it's not important. But it makes a difference for other algebras. So So like I said, we have similar properties like for the binary ones, monotone in each argument. It's below every argument. It plays well with subalgebras. And one thing to point out, maybe the k-array commutator of alpha 1 up to alpha k is always below the commutator of fewer congruences. You can kick out the first one. So it's below the k-1 array commutator of congruences alpha 2, alpha k. You have to be a bit careful about what you can omit here, because it's not symmetric under permutation of arguments usually, but you can kick out the first commutator, the first congruence. So with this, we certainly get a series of higher and higher commutators of the total congruence with one with itself, right? The binary contains the ternary, the four-array, and so forth. And now what it means to be n supernilpotent is that this series stops after n+1 steps. Okay. Like from what I said before, and some group theory, n supernilpotent and n nilpotent means the same for groups. Nothing to see here. Now, if you generalize a bit to congruence modular varieties, there a finite algebra is supernilpotent if and only if it's a direct product of nilpotent algebras of prime power order. So this decomposition, this was essentially proved by Keith in the end of the 90s. He didn't phrase it that way because the name supernilpotent was coined by Erhard Eichinger only later because precisely of this result. Right? Supernilpotent here in this setting of congruence modular varieties means nilpotent with some extra stuff, structure on this decomposition. Keith and Agnes showed that more generally, every finite algebra, supernilpotent implies left and right nilpotence as well. This finiteness is important in this result. More generally, in Taylor varieties, Andrew Moore had showed that every supernilpotent algebra is left nilpotent. But in general, that's not true. And so Matt Moore and Andrew constructed a specific example of a supernilpotent infinite algebra, which is not even solvable. And so things can go wrong if you go very far out of your comfort zone of Taylor varieties and finite algebras. All right. So finally, what can I say about nilpotent or supernilpotent semigroups? Of this result, a finite semigroup is left or right nilpotent if and only if it's supernilpotent, if and only if it's a nilpotent extension of a Riesz matrix semigroup, where the group that goes in this construction has to be a nilpotent group. So I should point out nilpotent, left and right nilpotent here, this is in the general algebraic sense. The nilpotent of the nilpotent extension, this is just what I described before, this semigroup theoretic nilpotence that products of length n are in this, fall into this Riesz matrix semigroup. Okay, so this is kind of the main new result that I wanted to show you. How do you prove this? Some ideas about that. First, the implications of that 1 or 2 or 3 imply 4. This is very straightforward. It's quite easy. If the whole semigroup is nilpotent, say, then like we said before, it can't contain any semilattices. This is a very strong restriction on the idempotence in such a finite semigroup. And using a bit of semigroup theory, this very quickly gives you the structure described in 4. The only thing that remains for a nilpotent semigroup, finite nilpotent semigroup, is to be a nilpotent extension of a Riesz matrix semigroup like this. The converse direction is a bit more work. So more interesting. So there we are given a semigroup that's such that, say, the product of any D elements is in a Riesz matrix semigroup. And additionally, we assume that the group G for that Riesz matrix semigroup is nilpotent of class E at most. Then we can show that this nilpotent extension is nilpotent in the general algebraic sense of class at most 2D plus 1. So this nilpotence degrees from the group and from the nilpotent extension, they add up. So get the nilpotence degree of the semigroup. And they multiply to give us the supernilpotence degree of that semigroup. So what I just want to point out from this result, the degrees, usually they don't match up. But nevertheless, this previous result shows that every finite semigroup that's nilpotent of some degree is also supernilpotent of some potentially other degree. I can't prove this directly. I can only prove this by going through this structure result, by explicitly characterizing in item 4 those semigroups, and then observe that the characterization of nilpotent semigroups and the characterization of supernilpotent semigroups lead to the same thing. So somehow I misjudged my time, or maybe luckily for you, I don't have time for a proof sketch. I'll just leave with a few open problems on this. So like I said, we still don't know what have a nice characterization of nilpotent semigroups in general. So this is only a question about infinite semigroups anymore, or solvable semigroups. We don't know. I mean, I know some things, random facts, like for free monoids, they are always left to nilpotent, weirdly enough. So free monoids are always solvable of degree 2. But in general, they are not right nilpotent. Of course, this is very far from saying that every monoid is 2 solvable, right? Because again, the solvability is not preserved by taking quotients. Another thing that one would be worthwhile to do is determine in general commutators of arbitrary congruences alpha and beta, or maybe just determine for given semigroups which congruences are central, and what are the congruences such that alpha commutator 1 is 0. There's some recent results by Michael Kenyon and David Stanovsky that they studied this for inverse semigroups. So for them, there's also a very nicer description for congruences, and they managed to characterize these central congruences in their recent paper. The one open thing that I'm really interested in is whether nilpotence and supernilpotence is the same for semigroups. It seems very unlikely, so I doubt that it's the case, but I don't have any counterexample in either direction, so that would be very nice. Just want to mention that, for example, for monoids, we can prove 2 nilpotents and 2 supernilpotents actually are the same. Right? I don't. Again, for monoids, I don't know about 3 nilpotents and 3 supernilpotents, whether they match up. But there's something in this direction that we know. And also, of course, the nilpotency and supernilpotency, this really in general does not have to match up, or even for a finite semigroup. Yeah, that's it, I think. That's all I got. Thank you.